Reaction mechanisms, lesson 12.6, and the worksheet, do all of it. Now, you're going to notice that when you need to download the worksheets right now, that one of the pages is a worksheet that I'm going to do for you the whole thing. The other one is one you'll do on your own. The notes that I have on this, my printer actually messed up. I have part of the notes. It starts with 12.6, but I don't really like how the notes. Well, the notes are important information. You could read through them. You could just read through them and get the information. But what I'm going to show you is really more important, I believe, just to go through a sample worksheet for you. And I had to put it on my phone because my printer's messed up. But anyway, what in the world is meant by reaction mechanism? Let me just start off and kind of tell you a little bit about this. This is one of the craziest, like, uncertain, advanced chemistry, theoretical chemistry for right now. We don't. This is an area where it's like we don't really know exactly what happens. In reaction mechanism, what you're trying to do, you're trying to map out step by step what happens when two chemicals, like for example NO2 and CO2, react to produce NO and CO. I'm sorry, NO2 and CO give you NO and CO2. Now, we know that there's collisions involved. I'm going to talk about that a little bit in a moment. There are collisions. Well, one thing, let's just say you have NO2. So let's put a little molecule of N and an O and an O. Now let's say you have a CO molecule. All right? Now, I'll draw it there. You know, these molecules could be anywhere around each other. CO could be there. How could they collide to be an effective collision? You might remember me saying that in the very beginning. They have to collide with the sufficient energy, activation energy, the sufficient energy to react, but they also need to collide in a correct way to form what's called the transition state, so that it can break off into these two. And I'll show you what I mean. Like if they were to collide with the carbon, the CO, if the carbon were to strike here, well, it will bounce, but there won't be any anything formed right there. In order to get these, most likely what has to happen is on NO, nitrogen dioxide molecule, a carbon dioxide molecule, the carbon needs to hit this O right there. So this CO needs to strike right there. Now, sufficiently enough so that, first of all, it kind of weakens all these bonds. That the NO could break apart, and also that it will be strong enough that it can attract right here. Then it can break off the ON to give you the the CO2. Trying to draw this. Hopefully you can see that. So the CO will bounce. You know, it can hit there too. The C could strike the CO, because C could strike there and pull off that O. Okay, so that might be what happens. We don't exactly know. It could be. Or it could be a crazy thing. You know, sometimes a molecule, the CO, maybe the CO, or it doesn't matter, it might strike this and knock the O loose. Then another CO comes along and says, hey, look at that O, and then grabs it. So what exactly happens? What is a step-by-step? Who breaks what, collides with what along the way? That is what a reaction mechanism aims to show. Now, I will tell you that this right here, if you start off with NO2 and CO, and if this is formed somewhere along the way, O-NO-CO, O-N-O-C-O, that would be an intermediate. Intermediate means this is a chemical, NO2CO, you could write it that way, or CONO2, that doesn't exist. It's not a reactant, and it's not a product. But you'll see what happens. It's produced along the way. All right, so that might be something that goes on. So reaction mechanisms try to describe all of that. Now, I'll show you this in the notes, the NO2, two elementary steps. Well, I'm going to talk about that in a minute. Two molecules of NO2 collide to form NO3. Well, okay, actually, there it is. It talks about it down there. It's something that I didn't even think to show you there. Two NO2s, oh, there it is. two NO2s, first they collide to make NO3 and NO. So it pulls one O off. Then the NO3 collides with CO2 to make CO to make a CO2 and NO2. There's actually it is. So I made up some other possibilities there, and it wasn't actually. You don't have to worry about what this one was. If you wanted to figure that out, you could. That's a neat thing. So it does make an intermediate there. All right. So proposed mechanism. Intermediate on the next page. A species involved that is neither a reactant nor a product. It's formed and consumed in the reaction sequence. I'll explain what that means in a minute. And then kinetics only considers what's called the elementary, rate determining steps. Okay. I want to skip down to one of the pages and mention something called molecularity. This term, as it mentions here, it talks about the number of species that must collide in order in a given step. Along the step, what must happen? Like if I said the NO2 and the NO2 have to collide to make an NO3 and an NO, okay? If only one molecule collides, we say it is first order. If one collision. Now that might even be like, okay, the reaction rate, yeah, first order. If two are colliding, the reaction is second order. Three would be third order. And that's very rare. Usually it's two things, one or two things can collide to make that happen. And zero order tells you that rate does not depend on the molecules at all. So there is a relation between what's called molecularity. I was reading that off the notes. Now, unimolecular, it just talks about this. It only, unimolecular, only the concentration of one reactant matters. And I gave an idea of H2O2. Bimolecular, Br2 and NO. Now you see me just looking down at my notes here. The speed of the reaction depends on the molarity of two things. All right, if it only depends on one thing. Okay, look at that. And you see under that four classes of molecularity. Unimolecular, H2O2 breaking down into oxygen and H2O. In that reaction, if you look on your notes, that's just a decomposition. Only one chemical breaks up. So that would be unimolecular. Only one thing's involved. But on the second one, you see Br2 and NO. Bimolecular, two are involved. And termolecular are very, very rare. It's number 3. Because it says three things, like we said, A, B, and C all have to collide. And then zero order, the rate is only dependent on K. And that's a strange one. It says mainly catalyzed, and I'll mention that to you as well. Well, I've talked about, if you see me talk about the catalyst before, they have a rate that does not depend on the concentration of reactants at all, on the rate constant. So those are the zero order ones. Usually catalyzed reaction. All right, and then it talks about proving a reaction mechanism. And I'm going to not, at this point, I'm not going to look at the notes. I'm going to go to the worksheet. Okay, so we'll look at the worksheet here. Let me even turn this thing off. Sorry, 1 second. I'm going to let this thing rest. It was really getting hot, overheating earlier. So, unimolecular, bimolecular, termolecular, and then the zero order one. All right, here we go. Let's try it. Let me see what we have on the worksheet. I made this out. I had the notes before, and I thought, this is kind of confusing. So what I'll do is, I'm going to go on this worksheet. The one that says, okay, here's what your paper says. I'm going to have to go from my own phone because my printer ran out. So everything happens at once. Computer overheat, everything. Okay. All right, good. My computer can rest a little bit. So there won't be any math in this, so maybe you'll like that. All right. There should be a Roman numeral 1 and a Roman numeral 2. NO2. Plus F gives you NO2F, right? Yeah. All right. Now, this of the two, this is one worksheet, and there's another worksheet. You'll do the other one on your own. This is like the worst of the two as far as how I organize it as well. Like my messier one. That's why I'm doing it myself for you. So there might be some slight changes I'll make on it. Okay, so it says this. The following elementary steps are proposed to represent the reaction mechanism for a particular reaction. Now, it says, they give you these two steps. I'll explain what all this means in a moment. It says, assume that the rate law is experimentally determined to be rate equals, all right, so I guess I'll write it up here maybe. Rate equals K times NO2, or times F2, molarity, then times NO2 to the second order. All right, so first order for F2 and second order for NO2. All right, so here's how this comes into play. First of all, let's say you've already done a calculation, like the ones we did on our past lessons or quizzes. We have the method of initial rates. You have all those things. Rate. You divide trial number 1, trial number 2 data by trial number 1, and you find the order 1 for F2. Then you divide trial number 3 divide number 2, and you find that NO2 is second order. So that might be one math way to get it to determine this law. Or it could have been from the integrated rate law, and you found that F2 is first order because it has natural log graph to show that, or NO2 is second order because NO2 has the inverse to show that. Okay, so you've already done the math. They've already figured out this is the rate law. Now we want to propose a mechanism step by step what occurs along the way. And so someone has proposed this. And what they often do is they normally give you 2 or 3 of these on the AP. Three possibilities. They'll say which one of these is most likely the correct mechanism for that reaction. Okay, so you have to prove it. Now, all right. Overall, you can see that overall, you just notice one thing, a side note. First order, second order. So overall, this reaction will be third order. Okay, so letter A says, what is the balanced overall equation for the reaction? Okay, so for a mechanism to be true, 2 things have to be true. Number 1, if these steps are true to describe this reaction, when you add these up, you ought to get the overall balanced equation. That's one thing. So they must match. So number 1, how about, I'm going to write this way. Is this mechanism, mechanism acceptable? It's kind of like, we can never know if it's true, the truth. But if we gave 3 of them, and only one of them is acceptable, the other 2 will cancel out for some reason. So the other 2 will not meet all this criteria. So only one will be the most acceptable. But even the most acceptable might not be right. There might be, like I was showing you those things that I was making up and I was wrong. And there's one on the paper that said, here's the actual mechanism. Well, that might even be wrong. We might find out later. But so far it matches all the criteria. Number 1, is this acceptable? Number 1, it must match the stoichiometry. You might write this somewhere else on the notes. It must match stoichiometry of the overall reaction. Now, since we don't have the overall reaction, I normally would give you that. But anyway, here's how you do it. Just add them up. NO2 and NO2 gives you 2 NO2s. Now notice this. Platinum is on the left side and it's on the right side. So guess what? That can just get canceled out. We don't need the platinum there. Another thing is the fluorines are going to cancel out. That one and that one. And I'll talk about what those are in a moment. The fluorine gets canceled out. So NO2 plus fluorine, F2, the fluoride. I'll just say the F monatomic fluorine. And that would be a very reactive, unstable thing. So I'm going to get to that in a minute. F2 gives you 2 NO2F. So that would be the overall equation. Now, what like I talked about how this reaction wasn't, this worksheet might not be the best. They might say, for this chemical reaction, 2NO2 plus F2 to give you 2NO2F. For this chemical reaction, the rate law is determined to be this by experiment. Okay, they could have that on one problem. You go A, B, C, D, E. You could do that. Then it could say, now, is this an acceptable mechanism for it? And you go through and you, first of all, we'll add them up. Yes, I get 2NO2, I get F2, 2NO2F. Yes, number one, it does match the stoichiometry of the equation. So it does give you a chemical reaction that's possible. Now, you wouldn't know it's possible except I just told you. But normally, on a problem, they would give you that to start off. So you say, hey, this is what happens. Does this match it? All right, number one, that first one is correct. Now, the second criteria has to be this. These are called elementary steps. Elementary steps. Okay. Elementary steps also have their own rate law. I'm going to erase this to do this next part. You can just do it down on the paper below. In fact, I'm going to put these back. I'm going to need this. Actually, I'm going to jump ahead and I might tell you what this F and PT are. You need to know about that before I go on. These are called elementary steps. Each elementary step has its own rate law. Elementary rate law. So, step number one, I don't have much space. Oh boy. I'll try to do it. I can probably do it in this small space right here. So step one, step two. Okay, before I do that though, let me go to my worksheet on the phone. And where do I ask you about F? Well, I ask you on letter E. So first, let's just skip over to letter E, and we'll do the easy thing first. It says, which species acts as a catalyst in this reaction? And justify your answer. Okay, a catalyst is a substance. It can be a solid, a liquid, or a gas. That chemical speeds up the reaction, but it doesn't actually take place in the... Well, how I want to say this. It's not a reactant or a product. Actually, it's both a reactant and a product. Like in this case, if it goes into the overall equation, like into the overall, platinum comes in as a reactant. I'm sorry, I said that wrong, kind of a weird way. Platinum is a reactant and it's a product. But it is not changed during the process. So it is not chemically changed to like platinum oxide or something like that. So that is a catalyst. By definition, a catalyst would be, as I said, anything that is unchanged, that within the elementary steps, within the mechanism. Let me write this down. What letter is this? Letter E. Platinum is a catalyst. I'll put within, that's better. Within the mechanism, if you want to even be better, within the two-step mechanism. Now, sometimes mechanisms can have 3 or 4 steps. Wow. So you might have to really look through all the steps to see this. But within the two-step mechanism, it is both a reactant and a product. Well, no, I better not say that. Don't say both reactions. It is unchanged. It is unchanged, chemically. That's I'm going to mix it up with the other one if I do that. It is unchanged. You can say it appears as a reactant and a product there too. All right. So it appears initially as a reactant and a product. I'm not going to write that out there. Okay. Well, as a reactant and product. All right. Now, I didn't ask you this. I'm going to do part 2 of this. Is there something about the intermediate in here? Oh, no. This is actually on letter B. I didn't see that. B says, which reaction intermediates are involved? And justify your answer. All right. All right. This appears, okay, first of all, the catalyst appears as a reactant and a product. I guess I better say that because I want to differentiate with the other one. And a product in the overall reaction. The main reaction. In the main reaction, 2NO2 plus fluorine gives you that. Platinum, you could put platinum there. Sometimes they even write PT above the arrow, meaning the catalyst is there. But it comes in PT and it comes out PT. But in the overall reaction, it's a reactant and a product, and it comes unchanged. The most thing is it is unchanged chemically. It goes in, comes out the same. That's the best way to know, the best definition. But for B, it says what intermediates are involved. An intermediate is a chemical substance that is produced along the way. Remember, I showed you one a moment ago. But then it is used up and it disappears. So notice this. It does not appear. Is there a chemical here that does not appear in this reaction up here that is produced and consumed? And you'll notice NO2 plus F2 in platinum gives you NO2F. Look at NO2F. It's not, oh no, it is there. I'm sorry. F. Look at the F. All right, I almost jumped at it. I wasn't looking at my paper. I'm just thinking. But F, NO2F is there. Okay, so it's not that. But F is produced, fluoride monatomic. And then, but we don't see it up here. Then on the next step, that monatomic fluoride joins with the NO2 to make NO2F. So this is it. F is an intermediate. It is not in the overall reaction. Well, that's one thing you could say, overall equation. But here's the most important. It appears as both, as a product. Let me see, how would you say it? It appears as a product and reactant. It is produced and consumed within the mechanism. It's probably better to say it that way. F is both produced, a product, then consumed within the mechanism steps. Okay, so F is produced in step number 1, and then in step number 2, it is consumed. Here it's a product, but then it becomes a reactant in the step number 2 of the mechanism, and it gives us your final. It's used to get to the final product. It is not in the overall reaction. So it is good to say it's not in the overall reaction, but it's both produced and consumed within the elementary steps. The platinum, on the other hand, even though we didn't write it up here, the platinum, you can put it above the arrow if you want, but it goes in. Originally, it went in the very first step, and then it came out there, right there. And now, you could even, it could even join on to something temporarily. So it's not impossible for a catalyst could also be part of an intermediate. All right, a catalyst can be part of an intermediate. I don't want to make it mixed up here, but the way you'll know it is platinum went in as platinum, and it came out as platinum also, okay? But the intermediate F did not even go in, so it wasn't a reactant. It was a product, then it was a reactant. So how about that? That's another way to look at it. The catalyst is a reactant, and if you want to call it a product, you could. It was really not a product. It's an unchanged product. It goes in and comes out unchanged. It's really, probably it's not the best to call it a reactant, a product, but it is. It's part of the reaction and comes out unchanged product. Reactant, then product. But an intermediate is product, then a reactant. So it's consumed. It's produced and then consumed. That one was not consumed at all. No platinum disappears. Okay, I want to get those two things out of the way first because those are kind of the easier ones. Oh no, you said the easier. So let's go back to the original question. Is this an acceptable mechanism for the chemical reaction 2NO2, F2 plus NO2, which gives you the rate law K shows fluorine to the first order and NO2 second order. Is this an acceptable mechanism? All right, so one thing that must be true is the elementary steps have to add up to give you, when you cancel out everything, cancel out all the intermediates and the any catalysts, cancel them out, you should get the overall balance equation, and you do. We showed you that we get this overall balance equation by adding those together. The second step, the second proof is a little bit crazier, and here I go. I'm going to write this down. First, I'm going to need to write down the elementary rate law for each of these steps. Oh, good, I have a yellow. I wanted to get this one. Okay, rate for this equation, this equation right here, rate is equal to K times NO2 times F2. Now, I'm not going to put platinum in it because it's not part of it. NO2 to the first power and F2 to the first power. I want you to see what I'm doing right here. It's kind of hard. You have to squeeze it on your paper. But what I've done, how in the world do I know that? Let me write this over here and I'll show you. NO2 plus F2. I'm just trying to move this over a little bit to have space. All right. Elementary step number 1. Elementary reaction 1. This is the rate law. So here's a rule about mechanisms. The elementary rate law, and if you want to call this, you would call it K1. In fact, I'll call it K1, step number 1. Rate equals K1, because this K is not the same as this K. All right? This is for this elementary reaction. Here's a cool thing. For an elementary reaction, the coefficients on the balance equation, 1 and 1 in this case, that's a 1 and that's a 1. They will be the powers, NO2 to the first power and F2 to the first power. So those coefficients will match only for the elementary rate law. Now, let me just tell you this right off, and I think I've said it before, but maybe not. Maybe the first time you've heard this. It is a coincidence. Yeah, I did say that before. F2 is to the first power. And notice there's a 1 there. And NO2 to the second power, second order, and it's a 2 there. Well, that cannot be relied upon. That's a coincidence. So for a chemical reaction, the only way to find the 1 and the 2 is by doing experiments. And I told you that means doing the math that we did before. An experiment. A lot of times that happens. That's a 1, that's a 2, and that's a 1, that's a 2. But it's not always true. However, for a mechanism, for an elementary step, that has to be true. Because remember, this involves kind of like the number of molecules that have to collide. And like 1 NO2 collides with 1 F2. 1 NO2 molecule collides with 1 F2 molecule right there. All right? And that matches it, okay? If it said 2 and 1, then that would mean 2 of these have to collide with that one. All right? So this matches the collisions. So the elementary step orders will match the coefficients in the elementary equation. All right. So that means that number 2, its rate will be we'll call it K2 times NO2. It's also to the first, because it's a 1 there, I'm sorry, I was going to use the yellow. I'm in a big mess. I'll call that K2. Now, some textbooks might show you about mathematically calculating the K, and we're not going to have to do that for a mechanism, so don't worry about that. All right, so there they are. All right, so let me just kind of put those aside for a minute. Here are the elementary step rate laws, and here are the elementary steps 1 and 2. So NO2 to the first, F2 to the first, NO2 to the first, F1 to the first. You know what? As I'm writing it, I think this is on your paper or somewhere else. I'm very sorry, but it is. Well, not okay. It was letter C. Write the rate law for each elementary reaction in the mechanism beside each. Oh, I wrote beside it. Okay, no, we did it right. I said to write it beside the equation. So if you can fit it beside, that's the best place. I think on the other worksheet, I give you more space to do that. Okay, then it says identify the molecularity of each, whether it's unimolecular, bimolecular, termolecular, and how many particles collide in each elementary steps. So we just told you that would be, overall, you could say it would be a bimolecular, two things will collide, okay? Bimolecular overall. You know, that one of these with one of those, one of these with one of those, okay? This with the intermediate, or this NO2 with the molecule F2. All right, that's all you would say there. Letter C. Molecularity. Now, okay, so here we go. Letter D, this is the crazy one. It says, identify the step. You might be having to watch this over again and roll back. We're at time 30 minutes, 27 seconds. Okay. Identify the step that must be the slowest in order for the mechanism to agree with the experimentally determined rate step. Okay. One little analogy, a side note, sometimes there could be not just one or two, but there might be 3 steps. Step 1, step 2, step 3. There could be 4 steps. Now, one analogy that sometimes people use is this. Imagine each step is like a funnel. So let's just say that you have a funnel. And I'm going to draw a funnel here. You know, but you can pour water through it. Here's one funnel. Then here's another funnel. And then here's another funnel. All right, now think about this for a minute. So if I pour and I fill this up, I try to fill this up with orange, whatever it is. Okay, so it's going to drip drop down into this, okay? Then it's going to fill this one up, and it's going to go through. And then it's going to go, it's going to just fall right through, isn't it? Okay, so tell me this. Which one of these was the slowest step in the funneling process? Step number 1, 2, or 3? And you'd say, well, certainly number 2. Look at that. Look at how small that funnel was. It's just going to be drip dropping through here. And then when it gets to step 3, it's going to shoot right down. In fact, funnel number 3 won't even matter with that funnel above it. Okay? This one takes a little bit longer because it has to all sink through, but not as long as that one. So this is called the slow step of a mechanism. In a mechanism, sometimes 2 molecules might just collide, boom, they break apart, and then they move on to the next step. But sometimes it might take a long time. You know, maybe, like we said, it's got to hit, they collide, nothing happens. They got to collide just in the right way with the right energy. Then we move on to the next step. Well, so the slow mechanism step is going to be the one that takes longer for those chemicals. One of these is going to be fast and one's going to be slow. We only had 2 here, but a lot of times there's 3 steps. So what you're going to do is you'll say the slow step is called the RDS, the rate determining step. The rate determining step is a slow step. And the reason why we need to know that, when you time a reaction, like you put the timer, you say, okay, when these react, it's going to all turn green. And I go, ready, set, right when you mix them, ready, set, go, mix them. All right, boom, green. Okay, we saw green after, 8 seconds or 5 seconds, whatever. We'll just say 8 seconds you saw green appear. Okay, all that you really were waiting on was for this one step. This was like instantaneous. There wasn't even any time involved there. This is gone. That one is a little bit. That one might have been 8 seconds. Or, maybe that was 7.5 seconds, and that was only 1.5, or probably even less. If that was 7.9, that was only 0.1 second to go there or something. Well, anyway, so it's not a perfect science of this, but when we measure in a lab, we're talking about the time that we're doing is to get the slowest step done. We assume that's the one that was the slowest step in the mechanism. Now, the slowest step determines the rate. There's one more thing about the slow step, too. I'm going to say this, and then I'm going to show it to you. The elementary rate law for the slow step, whatever the slow step is, this number 1 or 2, the elementary rate law can be used to derive the overall rate law. It will be algebraically proportional to the overall rate law of the equation. Those are some good words to use. How about say the overall rate law can be algebraically derived from the slow step in the elementary step, from the slow elementary step. The overall rate law for the reaction, which was rate equals K, F2 to the first, NO2 to the second, is algebraically proportional to the rate law of the slow step. It can be derived from it. I'm going to show you that right now. Now, there are some different ways to answer this question, but this, I think, is the easiest way. And no, I know it sounds like, what is he talking about? Okay, so first of all, let's figure that out. We'll be able to figure out the slow step, and we'll be able to figure out if this mechanism is any good or not. All right, so here's what you do. First, you look at step number 1. All right, and was there a question on the paper about what is a slow step? Well, we'll let you know that. Letter D just says, identify the step that must be the slowest, yeah, there it is, in order for the mechanism to agree with the experimentally determined rate law. Justify your answer. Now, sometimes there might not be any that agrees with the law, and it might be the wrong mechanism. So sometimes they give you a question, they give you step 1 and 2, step 1, 2, 3, step 1 and 2. They give you 3 options, and you got to find the one that is correct. This one, we're saying, okay, it looks like this is going to be correct, but show me the slow step. Okay, so here's what we'll do. This is the way I like to word it. Based on, I'll just start off with, let me see. Oh, there's something I did not show you. Very important, and I didn't draw it. Technically, for what we're doing in this problem, this needs to be a double arrow. This needs to be an equilibrium. Now, if you gave a choice between one had a single arrow and one had a double, go with a double arrow for what I'm going to show you right here. That's called an equilibrium. It's actually the next chapter. So you kind of need the next chapter before you can do this one. But the way it works, let me just do this real quick here, I hope. According to, all right, let me see this, NO2. All right, according to step 1, according to elementary step 1, all right, elementary step 1, the rate is equal to K1 NO2 to the first and F2 to the first. All right, now here's the deal. NO2 in the overall reaction should be second order, but here it's only first order. F2 is first order, and F2 is first order. Okay, it cannot be the rate determining step, because in the rate determining step, the orders for each of these have to match the order of the overall rate law. So NO2 is first order, and it is second order there, so it's not. According to step 1, rate equals that. So it is not the RDS, the rate determining step. NO2 this contains both reactants, NO2 and F2, and NO2 is only to the first order. But now, according to step 2, so we would say step 2 must be the rate determining step. According to step 2, okay, rate. Now, here's what I'm going to do. Rate is equal to, I'm going to change it to proportional in a moment. Rate is equal to its constant, K2, times NO2 to the first, and then times F to the first. Now, notice this. This time, NO2 is the first. However, don't rule it out yet, because there is no F2 in it. You might say, well, wait a minute. F is in it. That's different. Yeah, an intermediate. We have to substitute out the intermediate in this step. So here's what I'm going to say. According to step 2, the rate of the overall reaction would be, the rate of this would be proportional to. Now, there's a symbol proportional to. It looks kind of like the alpha in a way, but it's more like this. I used to be able to draw it. Yeah, it looks like that. Look for proportionality symbol in math, and it looks something like that. Or you can write, if you want to write the word is proportional to. According to step 2, the rate is proportional to K times the concentration of, well, it's actually, you can take the K out. The rate is equal to K2 times NO2 to the first, F to the first. But the rate will therefore be proportional to NO2 to the first order and F to the first order. But now, look at this. Based on step number 1, let's see how we got F. According to step number 1, okay, according to step 2, that. You know what? I should move this over. According to step 2, rate will be proportional to NO2 to the first and a first order collision, of the flora, of the of the atomic fluorine. But according to step 1, elementary step number 1, look at this. The concentration of F is going to be proportional to the concentration of NO2 times the concentration of F2. Now, what I'm going to do, F to the first power will be NO2 to the first power and F1 to the first power as well. I'm going to use the coefficients there at 1. That one I didn't even talk about. 1 and 1. It wasn't involved. But all right, now watch this. According to step 2, that's the rate law. But according to step 1, the production of F, you get one F produced from a single particle NO2 colliding with a single particle of F2. So a first order NO2, first order F2 colliding will give you a first order F. All right, everybody see how that works. So according to step 1, now you could almost, if you wanted to, you could almost like think of it as saying that equals NO2 times F is equal to NO2 to the first, F to the first, because it's dependent on that. It's really proportional. All right, so according to step 2, we get this. According to step 1, that. All right, then now say by substitution, or I'll put it here. I don't have space to do this. By substituting, I'll just put it. By substituting, here's what I'm going to do. The rate of step 2's rate law would show to be proportional to NO2 to the first, and I'm going to substitute F. So instead of F, since one of these F is single, and if there had been a 2 right there, I'd have to put a 2 here, okay? If there were a 2 there, I had to put a 2 there, and then I have to take the square root of both sides to solve for F to plug it in there. But since it's a 1, that makes it easy. F with a 1 coefficient is NO2 1, F2 1. So I'm going to substitute, instead of F, I'm going to take this out, and in its place I'm going to put in NO2 1, F2 1. All right? Now, when I put those together, it says rate is proportional to NO2 first, all right? Oh, no, NO2 to the second now, because I got 2 of them, and F2 to the first. All right. Therefore, step 2 is the RDS. And now here's the deal. So this is what I told you in the beginning. So is this an acceptable mechanism? Yes, it is. Because the overall rate law, K, F2 1, F2 first order, NO2 second order, can be algebraically derived from the elementary rate law of step 2. The elementary rate law of step 2 tells you this. But now, the rate law has to have only the reactants of the overall reaction in it. And since there's an intermediate, you have to substitute it out by putting in the things that form this. The formation of F was dependent on, the first order formation of F was dependent on first order NO2 and first order F2 according to step number 1 right here. One of these and one of those gave you that. All right, so you kind of look at that. For that matter, NO2 is also dependent on one of those and one of those. But NO2 does not have any effect on producing F. Only these two do. And don't even worry about and we don't put the catalyst involved. So F is proportional to NO2 and F. So what I told you was, first I said, according to step 2, this is the rate law. According to step 1, we can look at that and say, okay, F concentration would be dependent on or equal to single NO2 to the 1, F2 to the 1. And that's also a 1 as well. Now, by substituting, that's the third thing, substituting into step 2's elementary rate law, the rate would be NO2 first, and F will become NO2 to the first and F2. So we take these two in the place of F right there, okay? And now that gives you the overall rate law. So therefore, it's the rate determining step. So that means that this step is the slow step, and this one above it will be fast. Sometimes they're going to help you out on a problem, and they'll put fast, fast, slow. And the slow one, you got to use that one to substitute in and derive it. Wow, that's a lot. And it looks like I'm going to have to continue on with this because there's a few more things left to tell you. Let me see the time. Yeah, I'm going to have to continue on with it later on. So I'll have to do a part 2. But I got the hard part of it done. And so I'm going to talk a little bit more. I'll do letter F and beyond in the next little section. So, wow, what is this? So what you do, make sure you've written this down. Hopefully, I think you saw all this. I think you did, or screenshot it or whatever. And when you do a worksheet, you're going to do one that looks almost like it, but it's a little bit better. I think it has less error in it. This is crazy stuff, but hey, it's not hard. This is the easiest way. There's some other ways to do it, and some where you do a little bit more algebra stuff. But by doing it this method, proportional to, you can write the word is proportional to if you want to. But by using that, you don't have to put the k's in it anymore. Because even though the rate law is K2 for step 2, NO2, 1, F1, well, I can just say, well, it's the rate of that step will be proportional to NO2, 1, F1. I don't have to actually worry about finding the K. That's all that matters. You just got to show that it algebraically, you can derive this from the slow step. That's all you got to show. And then that means it is an acceptable mechanism.